Hello everyone. We have seen how to design a half adder using an XOR gate and AND gate to perform a 2-bit addition, right? In this video, what we are going to do is that we are going to implement the same half adder with the help of VHDL. Okay, let's do that. So we know the circuit diagram. So we have an XOR gate. Let me label this as U0. This will become handy when we start doing with VHDL coding. And let me call this second gate as U1. Okay, we have got two gates and we have got two inputs A and B, and we have got the outputs S and C. Now let us go to the Quartus interface. Here I have already created the AND gate and XOR gate the way that we have discussed in the previous VHDL video. So here you can see this is an AND gate, two input AND gate having two inputs I0 and I1, and the output being O0, and the input output relation is represented here. Similarly, the XOR gate is here. The only difference is that the entity name is different over here. I have used the same inputs and outputs, and here is the relationship between the input and output. Now we have to instantiate this in a higher level hierarchy. That is what we are going to do next. For that, I've already written half of the code over here. I have just written the library declaration and also the entity declaration. The entity name is half_adder, and here are my inputs A and B of standard logic, and the direction is in, and S and C are the out type, and that also it having data type of standard logic. Okay, now the architecture we need to fill here. Right. So in the previous video, when we discussed about the test bench, we have discussed that we need to give some sort of function prototype about the components, right, which are called components. Here, let us do that. Let us start with AND gate. As we did before, we will just copy paste the entity declaration from here to after the architecture. Then we will just align the stuff. These are some common practices which I used to follow, and I have to rename this entity as component, right? Here also I need to replace that with component. This is a component declaration now. Okay, so I have commented out for better readability. I would recommend that you follow the commenting usage. Okay, now AND gate is there. Now I also need to have the XOR gate. Let me copy paste this entity declaration the same way I did for the AND gate. Right, let me just make the alignment proper. Then comes entity, replace that with the component. Yeah, so the prototype is here, or the component declaration here. Now we just need to pick and place this component in the circuit, right? Okay, let us do that. Yeah, here we will have the same labels as what I have shown you in the diagram. So let's have U0. U0 is the label of that gate, and that gate is of type XOR_2. This is the name of the component. I'm going to instantiate that component, right? Then I can also I need to give the port map, right? So port map, then the inputs of this XOR gate are the A and B, which are the inputs of the half adder, and the output is S. Okay, if you remember from the circuit diagram, the XOR gate produces the S output. Okay, now we can end the statement by inserting a semicolon. Now we can have the second gate U1, and that's of type AND2, and the port map is given by A, B, and C, right? C is the carry out, right? Now that we have completed the code, By the way, this kind of coding style is known as structural coding, even though it has got no relationship with the architecture name, but we tend to use the architecture name either as behavioral, functional, or structural. Okay, so this is just to indicate that this particular architecture is of a structural type. It's not mandatory that you have to use this name. You are free to use any name for that matter. Now, what else we need to do? We need to make this as a top level entity, then compile by pressing Ctrl L, or you can also do processing start compilation by pressing this particular menu item. So it is processing the compilation. Let's wait. Yeah, there are no errors. And the first thing what we have to verify is that whatever we have compiled or synthesized, is it as per our need? Yeah. Press Ctrl and scroll. So you can see that there is a gate with a label U0 here, which is of type XOR2, and another gate and gate over here, which is of type, which is the label of which is U1, right? And if you just simply double click on this green box, it will just go down the hierarchy, right? And you can just control scroll, you will get, you will be able to zoom in and zoom out. Then again, if you once again double click the space, then that will go up the hierarchy. Okay, now that you have verified the netlist, now we are ready for the simulation, right? Let us do that. Again, you can click on the RTL simulation. Now that should invoke the model sim interface. Yeah, the interface is here, model sim interface is here. And as per what we did before, we just need to click on the work. Then there will be different entities. It will list out all the entities in that top level hierarchy, but we have to choose the top level hierarchy from that. Double click on that, and it will list all the objects inside the top level hierarchy, A, B, S, and C. Let us select all of them by pressing Ctrl A. Then if you do Ctrl W, all those will be transferred to the waveform window. Okay, by the way, if you click on this particular button over here, it will toggle between the longer names and the shorter names. Let us go with the shorter names. Okay, A, B, S, C. Now we can go ahead and force each of these inputs one by one. There is another shortcut. You can assign these as clocks. Okay, so I will just define this as a clock. This is not a proper way of doing, but this will get the job done. Okay, press OK. Then for the next input, what I'm going to do is that I'll define this as a clock, but with a different period. I'm going to have 150 as the period of this clock, right? So we have defined both the inputs. We don't have to touch the output. Let us run this code. 1, 2, 3. Yeah, 3 times. That's fine for the time being. Let us do zoom fit, and let us verify the truth table here. So here you can see that both the inputs are 1 and output is as sum is 0 and carry is 1. Fine. Let us go to the next value. Here for A is 0, B is 1, and you can see that S is 1 and C is 0. That is also expected. Here both inputs are zeros, and the output, both the outputs are zeros again. Yeah, that is also according as per our truth table. And here we can see that A is 1, B is 0, S is 1, and C is 0. And you can see that all the truth table combinations are verified like this. Okay, now let us close this window. Let me introduce one more type of simulation here. That is, either you can go here, tools, run simulation tool, then click on gate level simulation, or the shortcut is over here, gate level simulation. So you can press run here. So the difference between the gate level simulation and RTL simulation is that RTL simulation is kind of a logical level simulation. It doesn't involve the actual hardware inside the device on which we are going to program this VHDL code, right? But in gate level simulation, all these information of the gate level implementation will be there, which tells you that if there is a propagation delay from through the gate, okay, so all these gates are having capacitive elements in them. So even if you want to have a 0 to 1 transition, like just like this, a moment transition, in practice that is not the case. There will be a slow rise from 0 to 1. Similar to that, when a signal propagates through a gate, there will be a propagation delay from the input to the output too. So all these will be taken care of in the gate level simulation. Okay, again you have to click on the plus button near the work library item. Then you have to double click on the half adder entity. Yeah, now you can see that there are a lot more objects in this objects window, right? You can see that there are a lot more objects because in actual circuit all these objects are present. But for the time being we are just worried about the first four, which are the inputs and outputs which we have created, right? So just press select them and press Ctrl W. Then you have all the inputs and outputs on the waveform window. Again, as we did before, you can assign clock. Then for B also, I'm going to assign clock, this time with a different period. Yeah, then run. Okay. Okay, zoom fit just to visualize the waveform, and you can see that all the waveforms are as per the truth table. Here, for such a small design, you won't find any difference between the RTL simulation and GLS or gate level simulation. But with higher or like bigger schematics or bigger designs, you will be having some differences between the RTL and gate level simulations. And gate level simulation results are much more reliable, even though you verify the first level of verification is at the RTL level simulation. You have to make sure that the GLS simulation also passes without any errors for a successful design, right? All right, then we have designed our half adder like this. So this is how you could like write a VHDL code for half adder. With that, let me wind up here. Thank you.